Hello and welcome to my lab. Here in the corner of my lab I have an old laser sitting that I bought off eBay some time ago. It's a 55 watt neodymium YAG laser and it's lamp pumped, so an older unit, and it should output about 55 watts. It's an old medical laser and it's fiber coupled. Now fiber coupling is neat, but I don't have any fiber that goes with it, and actually I want a free space beam. So what I'm gonna do is I'm gonna take this laser apart, have a look what's inside, and take the head out and leave the power supply, the water cooling, etc. in the unit, and extend all the hoses and wires of the head so that I can place it on my optical breadboard. This way I have a laser on my optical breadboard without the rest of the unit sitting on top of it as well. So let's turn it on, have a quick look. Now there's some stuff in there, probably some old stuff related to the fiber coupling. Now as you see, it generates an error. That's because I don't have any fiber connected, but for this test run I was lazy and I don't even have the foot switch connected, so of course it's gonna throw an error. Now as we take it apart, we also have to defeat the mechanism of the fiber so that the unit actually believes that there's a fiber in there. I took it apart, I took the covers off, the laser head is already gone. You can see the two water cooling hoses there, I already extended those. So now we can see how it's built up inside. This is the main PCB, that's the front panel with all of the controls. See the big radiator with here the high voltage power supply that powers the arc lamp. And if we look in the back, you see the big fan and the water cooling pump. And the reservoir sits in the bottom of the laser. This is the filling tube, and the whole bottom of the laser is the water reservoir. And there are some more electronics around here, but nothing exciting. So this is the laser head. I already took it out. It looks pretty cool, and let's have a look around and see what we can find. At the back is a helium neon laser, so that's actually an extra laser bolted to the side. And this is a visible laser, 632 nanometers, and that's passed around the back and actually through the whole laser, and that way you don't need to combine the two wavelengths, you just shoot it through the whole laser cavity. And that works because the YAG laser itself, the neodymium YAG, works at 1064 nanometers, which is invisible. That's of course why you have the aiming laser. But also the mirrors don't reflect very much at 632 nanometers, so you can just pass that alignment laser straight through. Now the laser cavity is between these two mirrors, the output coupler and the high reflecting mirror, and in between here sits this big block, and inside here you have the neodymium YAG rod. That's the doped rod that is actually the laser crystal. Around it is a big reflecting cavity, so that the output of the arc lamp, you see the electrical connections of the arc lamp, that light is all reflected by this cavity to the laser crystal. It's probably an elliptical cavity, such that the light is properly coupled into the crystal. Now these two wires run to a separate box. This is the starter box, because the lamp runs at, I would guess, around 150 volts. But to start it, to actually strike an arc in the lamp, you need to ignite it with a high voltage pulse, and this box provides that pulse. Now on the output we also have a small power measurement unit, I guess, with a small pickoff mirror, and we have two safety shutters inside the cavity. It's a medical laser, but of course these kind of things you also find in lab lasers. So for safety and measurement purposes, you always have a shutter somewhere and a power measurement. Now you know how much power you're actually getting out of your laser. Now if you want to know more about how lasers work, 10 years ago I made a video together with Destin from Smarter Every Day on how lasers work. So if you want to see a 10-year younger me, then look up that video. As you can see, there is no shielding of the actual cavity of the laser, so if there's dust in there on the mirrors or on the end surfaces of the laser crystal, then if I turn the laser on, I'll probably burn the dust in and yeah, ruin the coatings everywhere. So that's a bad idea. So probably I'll have to take it apart to clean the whole thing, because well, if 55 watt comes out, imagine what the intracavity flux is, so I don't want to power it on just yet. So this is an intermediate shot of extending the cables. I've extended the hoses and the cables for the head. I didn't have a signal cable laying around with many wires in one cable, so I had to make it all of individual wires. That's what I had laying around. I also extended one flat cable. Now for now it's all tied up together, but I will put this into one big hose. Now for the remote of all the controls, I also needed to extend a 50-pin flat cable, and I decided to split up the flat cable in strands of 10 wires, such that when I bundle them it's a bit more like a round cable instead of one big flat cable. I found several of these red warning labels around the laser, and they tell you that these components that the label is attached to are not connected to the mains ground, and that if a fault develops in the unit, they can be under high voltage. Now, I guess the reason why they want to float these units is that switch mode power supplies, and especially a high power one like this arc lamp power supply, can be quite noisy, and dumping that noise onto the mains earth in a hospital environment may not be such a good idea. So all these components are mounted on insulated standoffs. Now this warning is actually quite relevant because the arc lamp is water cooled, and water and high voltage typically don't mix. Now of course demineralized water is used, and usually the high voltage and water are not in contact with each other, but if the arc lamp fails, and that can happen due to old age, it can break and water can enter into the arc lamp and come in contact with the high voltage terminals. So then you rely on the water insulation to actually keep the high voltage out. So it's good to realize that when you mess around with these lasers, you know what you're doing, because there is high voltage in there, besides of course the high output power optically. Now, when I was extending the leads of the laser head, I had also had to extend the wires of the arc lamp itself. Now what I used for that was actually wires that are also used for solar panels. These ones are 4 mm squared, and they're rated for 1.5 kilovolt insulation, which is plenty for this application. The original wire was rated at 600 volts, but of course if you extend wires you want to overdo on the specifications. The wire was actually relatively cheap for the thickness that I got. Now I also defeated the safety of the fiber, and I actually already lost the component that checks if the fiber is present, and I left myself with the connector just shorted, which tells the laser that there is a proper fiber inserted and that the laser is allowed to turn on. So I want to place the cable bundle into a single hose to have it more neat. Now the water cooling lines are the thickest. They have an outside diameter of 16 mm. So I bought a hose with supposedly a 32 mm inside diameter, but yeah, well, only the connector piece is actually 32 mm in diameter. So past that the inner diameter gets smaller, so that really doesn't fit. So well, I have to step it up a bit and I'll put it in this hose. And if you need to check if the hose is really 10 meters, just over 15 Hertz, sounds like 10 meters. So the hose I got was sold as a swimming pool hose, but as you can see it's remarkably similar to this hose, which is the hose of a Coherent Verdi laser head. Now that head has been cut off from its power supply, maybe in some future video I'll cover that. But it's interesting to see, and it's not a bad choice. Okay, now I'm gonna trim the frame a bit. frame is this high, but with the components back here I think I can reduce the height, so I'm going to saw this part off. And I'm going to do that hopefully without creating too much dust and other stuff. So the 50mm hole is done. Wasn't easy with a handheld drill doing a 50mm hole, but I think it was easier than putting the thing underneath the drill press. I've put the laser head here on my bench because I wanted to open it up. I'm very curious what's inside and I wanted to show it to you. And I wanted to check if everything still looks clean inside. The laser is water cooled and I've seen more than one laser that was pretty contaminated and ugly on the inside. So I want to check if everything is alright. And there you go, the inside of the laser head. Now it looks really cool. And we have here at the front the neodymium YAG rod enclosed in a flow tube. And the water flows inside there to cool the YAG rod, because a lot of power gets dumped into it, a lot of optical power, which means that it heats up and it needs to be cooled away. Otherwise it heats up too far, it fractures, or you get a lot of thermal lensing. Now, at the back you have the arc lamp. It's not a flash lamp pumped laser, it's an arc lamp, it's continuous. And that also is enclosed in a flow tube, because a lot of power is put into that arc lamp and that needs to be cooled away. Now there are two openings here for water cooling, because the reflector cavity itself is also cooled. Now, a lot of power gets dumped into that cavity and it's not 100% reflecting. So some of that power is absorbed and you don't want to have it heat up very strong, so also the cavity itself is water cooled. Now, I've seen lasers that are completely green on the inside, but this one actually looks really clean. I'm happy with it and I'm going to leave it as it is, and I'm going to close it up again. And there you go. It's back together again. Now, it's probably useful if I draw on the whiteboard everything we've seen so far to give you a schematic overview and to put it a bit in perspective. So let's start with the laser crystal. As we've seen, it was inside a flow tube. So those two are coaxially, with here water cooling the laser rod running through the flow tube. And the laser crystal is pumped by an arc lamp. So the arc lamp sits next to it, also in a flow tube, because the arc lamp dissipates a lot of heat and this heat needs to be cooled away. Now the arc lamp generates a lot of light that is coupled into the laser crystal. And here the neodymium atoms are excited to their upper state. So the arc lamp pumps the laser rod. Now to make a laser we want to place a cavity around it. So on one end we place a high reflecting mirror, and on the other end we place an output coupler. Now the high reflecting mirror is, as the name says, high reflecting, and the output coupler is only partially reflecting. Now I don't know the number of this laser, I haven't measured it yet, but I would guess it's around 90% reflective. So most of the light that meets the output coupler is reflected back. Now the idea is that if a neodymium atom here emits light, and it does so in a cavity mode, so in a direction and position that bounces in between the two mirrors, then each pass that it bounces around, it gets amplified by the other neodymium atoms that are pumped by the arc lamp, and this continues, and this beam, each round trip gains intensity until it actually depletes the upper lasing level of the neodymium YAG rod, and then you get this powerful circulating beam. Now, of course you want to have a useful beam out, that's why this mirror is partially reflective. So each round tip part of the beam is coupled out. Now, as we've seen, there was also this helium neon laser alignment, this alignment laser off to the side. So here we have this alignment laser, and via two folding mirrors it was sending its beam straight through the laser cavity. This way they are aligned with each other, but also the alignment laser is 632 nanometers, which is visible. This means that you can actually aim your laser. The neodymium operates at 1064 nanometers. So these two mirrors work for 1064 and are largely transparent for 632. So you can just shoot the 632 through the whole laser cavity with no issue, without having any special beam combining optics. So now I'm gonna draw a different view of the arc lamp and the laser rod to give a bit better idea how this pumping actually works. So now we're gonna look basically straight into the laser, something which you should never do. And then you have the laser crystal here, concentric in the flow tube. So this is where the water is. Next to it is the arc lamp, also in a flow tube. So around it it's also water cooled. And to get the light from the arc lamp into the laser crystal, it's enclosed in a elliptical cavity. So if we emit light here, it reflects straight into the laser crystal. And this works for actually every angle. So no matter where the light emits from the arc lamp, everything is reflected back into the laser crystal. Because an ellipse like this has two focal points, and if you put the laser crystal in one focal point, the arc lamp in the other focal point, the light is perfectly coupled from the arc lamp into the laser crystal. I made 3 feet for the laser head out of a thick aluminum plate, and I machined slot holes in them, so that I could always find a matching hole on the optical breadboard. Now, I was worried that dust may have gotten on the optics, as there are no beam pipes shielding the laser cavity. So to check the state of the optics, I placed a beam splitter cube in the cavity to look around the corner into the optics, and the beam splitter gave me some flexibility in illuminating the optics. Now, looking through the beam splitter with a macro lens on my camera, I see that there's dust on the cavity mirrors. Now, I tried to clean the optics in place, but cleaning optics inside a deep hole is quite difficult. So the mirrors improved a lot, but still some dust remained. So this is after the second cleaning attempt, and it looks pretty much like after the first one. So I don't think I can improve on this. Now, I didn't like that I still had dust on the mirror that I cannot take out if I leave the mirrors mounted like this. So I want to disassemble the mirror mounts, clean the optics as best as I can, and put it back in. Now, if I'm going to take out the optics, I will lose the cavity alignment. So I want to check, can I measure this cavity alignment and make sure that if I put the mirror back in, I can align it properly again. So what I'm doing is I have this alignment laser aligned such that it points straight into the center of these optics. Now, if the back reflection ends up perfectly back into the laser again, I have it set up perpendicular to the optical surfaces. Now, mind you that not all lasers can take a back reflecting beam. but Heenies are quite robust and they have no problem with it. Now if the beam goes straight back into the laser, you don't really see it anymore. So what I did is I placed a beam splitter cube halfway, such that the back traveling beam, part of it is split off to this white box. You see a very bright spot here. Now these are actually 3 spots, because I have back reflecting beams from the output coupler, the laser crystal and the high reflecting mirror. And all of these will travel back. And because all those surfaces are parallel and the laser is perpendicular to them, all the reflections will also be perpendicular to the optical surfaces and collinear. And that's why we see here 3 spots on top of each other. Now this is just a very dim spot, that's an internal reflection of the beam splitter cube. Now if I detune, for example, the output coupling mirror, we should see that these spots change. See if I can zoom in. So I will now rotate it by like a quarter of a turn. And you see spots moving, they diverge a bit. But if I rotate it back, it all ends up in the same place again. So this means that I can check if my alignment is good and I can correct it if needed. So now I'm confident that I can take out the mirrors of the laser, but still be able to align them back when I put them back in, because if you put them back in with these mountings, it's not entirely reproducible. So if there are very small deviations, I have to adjust it. But at least now I know, since I get these individual reflections, that I have something to look for when aligning the system. If there were, for example, significant wedges on the optics, or if the laser crystal had Brewster angle ends, which I wouldn't expect, then I would not get very nice reflections, and aligning it might have been a lot bigger pain. There you go, there goes the optic. You can see this one has this triangle pointing to the coated side. In this case the back side. In this case the back side doesn't have to be coated at all, but it's quite typical that the front side of the optic is marked with a triangle like that. Now when I handle these optics, I'm wearing gloves to make sure that I don't contaminate them. Also I handle them by the edges, because even with gloves you don't want to touch the sensitive coatings. But if it's not that critical, you can handle them without gloves. Then you have to be really careful not to touch the front surface of the optic, because that will contaminate them. Single drop of isopropanol. And drag it across the optic. You can see actually I have too little solvent in there, and now it already evaporates. So that's a lot more, maybe a bit too much. But now at least the whole surface is covered, and only when I drag the paper off it becomes dry, instead of drying up as it is on there. Because you want this effect of pulling the solvent out of there. There you go. And of course the other side. And there we go. We've cleaned all the optics. Now I only have to check the alignment of the high reflecting mirror, but other than that, the laser head is ready. Now let's look at the alignment. I'll jiggle one knob. You'll see that spot is the output copper reflection. And you see it here even misses the exit aperture of the alignment laser, and it should go straight back into the laser, and it should go onto these two very small spots. And there you go. It's now properly aligned again. I've cleaned the high reflecting mirror. It's now time to put the parts back. I've put a short stretch of tubing around this beam pipe so that it extends a few millimeters, and it will create a bit of a seal against the shutter housing, while also providing vibration isolation just like these feet do. Now I've only chosen to extend a few millimeters because this stretchy hose might narrow down a bit away from the beam pipe, but if it catches the laser beam, it will absorb power, heat up, and that might burn or create fumes, and that would be really bad. On the other side, I created a small stretch of beam tubing, which I can mount with a set screw, and this will sit very close to the shutter housing, but not actually touching it. Now this way it will be very difficult for dust to actually find its way in and make its way to the optical surfaces. So this is roughly how it will be after I assemble it. Now that the cavity is done and nicely shielded, the next step is to connect the hose with all the electrical connections and the water cooling. Okay, I finished hooking up the laser head. I still have to mount the box with the starter electronics to the laser head, and I want to build an enclosure for the head. All these electronics you don't want to touch, especially not the high voltage terminals of the Hini laser, and all the optics of course also need to be shielded from dust, a lot more than they are now. I finished the remote control. I built it all in this box that I had laying around. It's a bit bigger than needed, but it works. And I simply glued in the original control panel. And here I have the emergency off switch and the key switch to turn it on. And instead of a foot pedal, I now have a simple rocker switch. So I don't have to keep a pedal down while I'm working, but I can simply switch it on. But for a medical laser it won't run continuously for very long durations. So I don't know how long the laser can run continuously. It has a temperature scale up here, so my guess is that for long runs eventually the temperature will increase too much and the laser will overheat and shut off. But I will find out. The laser is now all set up. I have the power supply unit here sitting in front. On the bench with the optical breadboard I have the laser head that's pointed into this old power meter head. I don't have a really good power meter for powers above 10 watts, so I have to use this old head. I connected it to this Newport readout unit and put in the calibration factor of, in this case, 0.4 millivolts per watt. And it should be good enough, otherwise it makes a good beam dump. Now there's a very good chance that it won't work. This project has been running for over the course of several months. Only somewhere in the beginning, after I already took the laser apart, I decided to make a video about it. And for many of the wiring, I had to order parts along the way, and then the project sits still for the delivery times, and I didn't have perfect bookkeeping on every wire, and I had to redo some. So if I made a mistake, it may not work at all. But I think I got it all, so let's see if it works. E3, new error. Let's try again. E7, again a new error. Now I've tried my best to find the cause of the E7 error, but I have no clue. I checked a lot of connections, tried a lot of debugging, but I don't even know what to look for and what E7 is related to. Of course, I've got no service manual for this thing. So at this point I would need to go back in time and look what the original laser was and the original signals and compare them. But yeah, all I know is that this laser has been working, but it's not working anymore. Well, I did tell you that I started filming this project about halfway, and I did have a laser in one piece during the introduction. That's because I bought two of them. After I bought the first, sometime later the second one surfaced on eBay, and I decided, well, what's better than one laser? Two lasers. So this one is unmodified. Only the water cooling is not working. It throws the E2 error and the pump's not running, so hopefully I can fix this one, only then to check how it's supposed to work, to be an example for how this one's supposed to work, and hopefully then I can fix it. I found at least one error that I made. I'll show you my thought process. So when I turn on the laser, the pump starts, and above the pump the contactor enables and immediately disables. You see the black pin jumps in and then pops out again. Now what is connected behind that contactor is the lamp power supply. So I was thinking, what if the lamp, for example, doesn't ignite, and then the power supply turns on, there's no ignition, and it turns off. So I was measuring the lamp voltage when I was looking at the head, and then I noticed I wired up the starter wrong. Of course, it's not much use if you document your process, take photos along the way, but then wire it up wrong and not look at your photos. As you can see, I wired up both wires from the power supply straight to the two terminals of the lamp, whereas this one is supposed to go to the terminal on the left, because the starter should be in series, so that the high current can flow through the lamp, but the starter intermediate starter can kick up the voltage during starting so that the lamp actually ignites. So perhaps E7 is just the code for the lamp is not igniting. So I'm going to fix the wiring there, and hopefully then I have a working laser. You can see here a very thick post. This is the terminal of the lamp that will go to high voltage when starting. When I wired up the ignition box wrong, I may have fried the power supply. So as a test, I now have my laser, the power towards the power supply diverted to the other laser, including all the control signals. So now this laser will start up, thinking that this is its power supply. If it can ignite the lamp in this head, then I know that the power supply is fine. The ignition box I already swapped between them, so those are both fine. And then I know that the problem will be in this power supply that I now bypassed. So I'll now fire up the laser, and if the lamp ignites, I'll quickly shut it off, because I only hooked up the power supply of the other laser, but the water cooling of it won't run. And I don't want to have a lamp running hot in water that stands still. So here we go. very quickly turned off the laser, but you could see that there was some light leaking out of the reflector cavity, and that light indicates that the lamp has ignited and the ignition is sustained, so it actually works. So I'm gonna have to do a power supply swap. Of course, when operating such a high power laser, laser safety is very important. The laser can output 55 watts in a beam of, I would guess, about 5 mm in diameter, so that's several watts per square millimeters and a pretty big power in total. Now, if you look in the laser safety standard, then the rating of the goggles should be at least L6. So you're looking for the D for continuous wave lasers like this. At 1064 nanometers, the L6 protection protects you up to 10 watts per square millimeter. And for L5 it's only 1 watt per square millimeter, which is definitely less than this laser can output. Well, these goggles can do L8, because these are really quite strong, thick filters, steel insert, so these will be absolutely fine. The power supply has been swapped. Now the whole unit is together again, the other laser is not attached anymore. So let's see if now we have a working laser. Press ignition, and we have a power readout. Aiming laser on, main laser enabled. Let's see what the power is that we get out. And very nice, 20 watts. So it works. I now have a fully functioning laser head on the table, remote control separately on the table, laser unit over there. All I now need to do is put the casing back on there, find something to build over the top here, put this in the casing, and then it's done. It's quite a small effect, but I believe that the switch mode power supply actually has a buzz to it that is depending on how much power it outputs. Now this laser has a photodiode to couple back what power it is outputting, so it's regulating for a constant light output. And with a constant light output and a varying cavity alignment, it means that the power supply needs to output a variable power to keep up with the cavity misalignment to keep producing the same output power. So I went for the lowest pitch I could hear, the lowest tone, and I believe that was the switch mode power supply outputting the lowest power, which meant it had the highest efficiency, the highest electrical to optical efficiency. And with that setting I indeed could go to the highest optical powers, because the whole system was optimized for efficiency. I finished the case for the bottom module. So this one houses the power supply, the water cooling, all the electronics, and I now put a case around it. As I took the laser head out, there was a big hole left in the case, so with some paneling I closed it up and I gave it a quick paint job. I also finished the case for the laser head. I used some 3D prints to get regular shapes around the laser head such that I can properly close the paneling around it. I even put the original sticker on top of it. That's the laser safety sticker. And now this laser head can be very conveniently used on top of my optical breadboard. So I now can screw this unit down, route the beam across the breadboard and use it for experiments. And I don't have to put the whole unit on top of it, that just would not work. I also didn't have the original fiber, and coupling into a fiber, out of a fiber, it's always lossy and it's not really the original beam. It can clean it up but only with loss, so it's not ideal. But now I can work with the laser, I have the remote control here, and I never have to worry about what's underneath the table. So I really enjoyed this project. I learned a lot, how the laser is built, how to modify it, how to repair it if I broke something. So that was a really nice experience. So I hope you enjoyed. Thanks for watching, and I hope to catch you next time.